Introduction to image enhancement using spatial domain. First, let us understand what is image enhancement. Image enhancement is a process that improves the quality of an image for a specific application. So, depending upon the application, the quality of the image will be improved in image enhancement. So, the reason for image enhancement is to highlight the interesting detail or important details in an image, also to remove the noise from an image, and also to make image look more appealing. There are three methods that can be used for image enhancement. First one is spatial domain, second one is frequency domain, and third one is combination method. The spatial domain deals with direct manipulation of pixel values. The frequency domain deals with modifying the Fourier transform of the image. In this frequency domain, the image will be converted from spatial domain to frequency domain. Then it is processed using Fourier transform. After processing, the image is converted back to spatial domain. Third method is combination method, which is combination of first and second method. Now we will understand the spatial domain. The term spatial domain refers to the image plane itself. If you consider an image with pixel values, so if you consider an image as it is, we will call that as spatial domain. So the image with pixel values are nothing but spatial domain. The image processing in this domain is direct manipulation of pixel values of an image. There are two categories of spatial domain. First one is intensity transformation, in which the modification of intensity values of pixel will take place. And second one is spatial filtering. Here there will be direct manipulation of pixels using a mask. The spatial domain technique operates directly on the pixels of an image. The spatial domain process is denoted by g of x comma y will be equal to t of f of x comma y. Here f of x comma y is an input image and g of x comma y is the output image, and the term t is known as the operator. This operator can be applied to the single image or to the set of images. This figure shows the basic implementation of this equation on a single image, which means the operator is applied on a single image. The point x comma y is the arbitrary location in an image, and the region next to this pixel is known as neighborhood of this pixel x comma y. In spatial domain processing, the spatial domain process consists of moving the origin of the neighborhood from pixel to pixel and applying the operator t to the pixel in the neighborhood that will be yielding the output of the location. If we consider this pixel with the neighborhood pixel, so this will be moved from this origin and the operation is performed on this based on the operator, and once the operation is performed, this pixel x comma y along with the neighborhood will be moved to the next pixel value, and then the operation will be performed.
In this lecture, let us understand some basic intensity transformation functions. The intensity transformation function is also known as gray level transformation. The intensity transformation are the simplest form of all image processing techniques. It can be represented as S is equal to T of R, where R is the value of pixel before processing and S is the value of pixel after processing. So R is the pixel value of input image and S is the pixel value of output image. Here T is the transformation that maps R with S. So the transformation function T will map the value of R with the value of S. Since we are dealing with digital images, the value of transformation function are stored in one-dimensional array. If we say one-dimensional array, which is nothing but in matrix form, so the value of transformation functions are stored in matrix form. The mapping of the value R with S is implemented through some lookup table if we consider 8-bit environment, the lookup table will consist of 256 entities, because 2 to the power of 8 will be equal to 256. At that case, we can have the transformation function from the value 0 to 255. So, if we take from 1, it will be up to 256. We will take the value from 0 up to 255. Figure shows 3 basic types of transformation function that are frequently used for image enhancement. We can classify the transformation function as linear transformation function, logarithmic transformation function, and power law transformation function. Linear transformation function consists of image negative and image identity. Logarithmic function consists of log function and inverse log function. Power law consists of nth root and nth power. In this graph, in x-axis we are taking r, which is input pixel values, and in y-axis we are taking s, which is output pixel values. So, we represent that as intensity levels of input pixel and output pixel. Intensity level, which means it is gray level. We take the total length of the gray level as L. So, we will represent that as 0 to L minus 1. So, that is why in the graph we have taken that as 0 to L minus 1. So, in between we have taken different values for L. In this graph we can observe 0 represents black and L minus 1, which is highest intensity level value, is white in x axis. It is same as in the y axis, where 0 is represented as black and higher pixel value is represented as white. First, let us understand the image identity in linear transformation function. Image identity is very less helpful in digital image processing, because the output image will be same as input image. That is why it is known as identity transformation. If we observe this graph, it is a linear graph. You can see it is a linear straight line. Here, if we map the input pixel value with the output pixel value, you will get the same value here at the output also. For example, if we consider the pixel value L by 4, if we map that to the identity line, and if we map with the input and output, we will get the input value as L by 4 and the output value as L by 4. In the same way, for L by 2, if we map with the input pixel value with the output pixel value, we will get the same pixel value, which means if you perform image identity, the output image will be same as input image, which is very less helpful in digital image processing. Now, let us understand image negative, which is another form of linear transformation function. In image negative also, the intensity level is taken from 0 to L minus 1. The image negative can be represented by the function s is equal to L minus 1 minus r. In image negative, the intensity value or pixel value will be reversed to produce an equivalent photographic negative. So, to produce a photographic negative, we will use the image negative transformation, which means it will give the inverse value of the pixel. For example, if you see here, 0 is nothing but black and L minus 1 is nothing but white. If we map this 0 with the output value, it is nothing but L minus 1. And if we map this L minus 1, which is white, with the output value, it will be 0. So, which means in image negative, black is converted into white and white is converted into black. For example, if we take r value as 0, if we take r is equal to 0, if we substitute here, at that case we will get s is equal to L minus 1. So, if r value is 0, s value is L minus 1. So, 0 is nothing but black. So, black is converted into L minus 1, which is white. In the same way, if we take r is equal to L minus 1, at that case s will be equal to, if we put L minus 1 here, so s value will become 0. So, if input pixel value is white, output pixel value will become black. So, this is the function of image negative. Now, let us understand the logarithmic transformation, which is also known as log transformation. The log transformation can be represented as S is equal to C log of 1 plus R. So here C is the constant which is scaling factor in this equation, and R value should be greater than or equal to 0. Here we have taken 1 plus R instead of R, because if we take log R, at that case if the value of R is equal to 0, log 0 will be equal to 0. That's why instead of taking log R, we have taken the value as log 1 plus R. With the help of logarithmic transformation or log transformation, we can compress the gray level or expand the gray level. So the same function can be performed using power law transformation also. We will see in the later part of this lecture. Now coming to logarithmic transformation, at the output of the image we can get higher contrast image or lower contrast image depending upon the function which we perform. For example, if we consider the logarithmic transformation graph here, which is in the form of a curve, if we take the input pixel value as L by 4, let us take the input pixel value as L by 4, let us map with that curve, and the output pixel value somewhere we will get here. So this is the output pixel value and this is the input pixel value. So if you observe, the input pixel value is narrow and we will get the wider output pixel value. So input pixel values are less and we are getting the output pixel value as higher pixel value. The higher pixel value will produce the higher contrast image which will enhance the image. So this is the function of logarithmic transformation. And for inverse log transformation, if we take pixel value, let us take 3L by 4 as the pixel value, and if we map with the output pixel value, we can see here we are having the wide input pixel values and we will get narrow pixel output values. So for higher input pixel value we are getting lower output pixel value in case of inverse log transformation. So this will produce the low contrast image at the output. So the logarithmic transformation will produce high contrast image and inverse log will produce the low contrast image. And this region of the graph are unaffected by the logarithmic transformation. So this is one thing you need to remember. So some part of this graph is unaffected by the logarithmic transformation. Now we will see the power law transformation, which consists of nth power and nth root. This can be represented as S is equal to CR to the power of gamma. Here if the gamma value is greater than 1, it will act as nth power. So if gamma value is greater than 1, so the lower part of this graph represents the nth power. So the power law will act as the nth power transformation, and if gamma value is less than 1, the power law will act as nth root transformation. It is also known as gamma correction since we are using the constant gamma, and this transformation is similar to the logarithmic transformation but different values of gamma. So for example, if we take the input pixel value here and if we take gamma is equal to 0.67, so we can map here with the input and output. So here you can see we are having less pixel values and at the output we are having high pixel values, which means at the output we will get a high contrast. For the same input pixel value, for different value of gamma, let us say gamma as 0.20, at that case we will get more contrast value compared to gamma value which is 0.67. The input pixel value will remain same. If we vary the gamma value, we will get different high contrast level if we take nth power transformation. In the same way, if we take this pixel value and gamma value as 2.5, if we map that with the input as well as output, input is having higher pixel value and output is having less pixel value, which means it will produce low contrast image at the output. In the same way, you can use the same input pixel value for different gamma value to get different low contrast output image. So this is how the nth power and nth root will operate in power law transformation. This is about basic intensity transformation function. Hope you have understood the topic. Thank you. Piecewise linear transformation function. There are three types of piecewise linear transformation function. First one is contrast stretching, second one is gray level slicing, and third one is bit plane slicing. First, let us understand the contrast stretching. Contrast is nothing but the difference between the highest gray level and the lowest gray level of an image. Many times we obtain low contrast image due to poor illumination or due to wrong setting of lens aperture in a digital camera. Hence, that effect can be overcome using contrast stretching. The basic idea behind contrast stretching is to increase the contrast of an image by making darker portion more darker and brighter portion brighter. So the darker portion in an image will be made more darker and the brighter portion in the image will be made more brighter in case of contrast stretching. This is the transformation that represents contrast stretching. From this transformation, we can identify that it has three lines which are linear. You can see from 0 to this point and from this point to here and from this point to this point. So three individual lines which are linear, and it has a same slope from 0 to r1 comma s1, and it has same slope from r1 comma s1 up to r2 comma s2, and it has same slope from r2 comma s2 up to l minus 1. So we can have these following analysis from this graph. So in this graph, if we make r1 is equal to s1 and r2 is equal to s2, at that case this function will act as linear transformation. Linear transformation, which means that will be a straight line. In linear transformation, there will be no change in the gray level values of an image. So if linear transformation is performed, there will be no change in gray level of an image. The second analysis is when r1 is equal to r2, s1 is equal to 0 and s2 is equal to l minus 1. At that case, this function will act as thresholding, which means if we make r1 is equal to r2, at that case in the x axis we are taking input pixel level, y axis it is the output pixels. If we make r1 is equal to r2, we will get a straight line. If s1 is equal to 0, if s1 is equal to 0 and s2 is equal to l minus 1, so this is s2 l minus 1, so at that case you will get a straight line like this. So this is l minus 1. So let us take this as s2. So this is s1 which is 0, s2 is equal to l minus 1, r1 is equal to r2. So if you observe this transformation function, this is nothing but a function that represents binary image, where this region represents black and this region represents white. So we can say in thresholding it will produce a binary image which will be having 0 or 1 as the pixel value in the output image. Now if we have intermediate values for r1 s1 and r2 s2, that will produce various degrees of spread in gray levels. So it will produce some spread in gray level, which means it will take different values of the gray levels if we take the intermediate values. Generally r1 will be less than or equal to r2 and s1 will be less than or equal to s2. At that case, the function will be having single value and it will be monotonically increasing function. If we take this example, in this example figure A shows the transformation function, figure B shows the low contrast image where you can see the image is not properly visible. Image C is the result of contrast stretching. So this is the output of contrast stretching, and if we perform thresholding on the image, so this is the output. So these are the results of contrast stretching. Next one is gray level slicing. Gray level slicing is used to highlight a specific range of gray levels in a given image. If we want to highlight some specific gray levels, at that case we can use gray level slicing. It can be implemented using two approaches. The first approach is to display a high value of all gray levels in the range of interest and low level value for all other gray levels. So, this transformation again will produce the binary image where region of interest of gray level will be having a high value and other gray level value will be very low. For example, you can see here the range of pixels between A and B are having high value and other pixels are having the low value. The second approach is to brighten the desired gray level but preserve the gray level unchanged for other pixels. You can see here, for example, here the values of pixel between A and B is given higher value or it is highlighted and other pixel values are kept as it is. So, it is similar to the straight line or a linear line of identity. You can see up to this point it is a identity straight line. So, the value of pixel value will not change, again from this point to this point the pixel value will not change. So, the only pixel values that will change is between the range A and B. So, this is the second approach. Let us take an example to understand gray level splicing. Figure A is an image on which the gray level splicing will be performed, and this is the resulting image after performing the gray level splicing using first approach. In first approach, only the desired pixel values will be having the higher value and remaining pixel value will be having the lower value. If you compare these two images, you can see this region should be highlighted and remaining region should not be highlighted in this image. So, that is the process that has been done. Only these pixel values are highlighted, remaining pixel values are made as 0. The next type is bit plane splicing. The bit plane slice can highlight the contribution made to the total image appearance by specific bits. For example, if we take a 8-bit image, this image is composed of 8 1-bit planes. As you can see from this figure, so we have taken an image and it is an 8-bit image, and this image is represented by 8 1-bit planes. So, bit plane that are ranging from bit plane 0 up to bit plane 7. Here bit plane 0 is LSB, which is least significant bit, and bit plane 7 is MSB, which is most significant bit. The higher order bits, especially top 4 bits, contains majority of visually significant data compared with the other bits. So, the top 4 bits will be having more data with respect to the image compared to the lower bits of the image. Separating a digital image into its bit plane is useful for analyzing the relative importance played by each bit. Also, this method is useful and used in image compression. So, this is the example of 8-bit image, and this figure shows the 8-bit plane of image. You can see the number at this bottom right. So, this is bit plane number 0, bit plane number 1, 2, 3, 4, 5, 6 and 7. So, if you observe, top 4 bits will be having majority of visually significant data. This is about piecewise linear transformation function. Hope you have understood the topic. Thank you. Is the graphical representation of any data. Histogram in case of image processing is used to represent the data related to digital images. Histogram is the representation of relative frequency of occurrence of the various gray levels. So, it represents how many times the gray level value has occurred in a given digital image. Let us take this as an example. This shows a digital image with various gray level. In this digital image, we do not have any gray level which is having value 0 or 1. That is why we have written the value as 0. Gray level value 2 has occurred 3 times, 3 has occurred 4 times, 4 has occurred 4 times, 5 has occurred 5 times, 6 has occurred 6 times and 7 has occurred 4 times in this digital image. To represent the histogram, we can take an x-axis with different gray level values from 0 to 7. So, 0 and 1, the value is 0. So, that is why we will represent it by 0. 2, 3 times it has occurred, 3, 4 times it has occurred, 4 times it has occurred, 5 and 6 it has occurred 5 times in a digital image and 7 has occurred 4 times. So, this is the histogram representation of the given digital image. So, this is one of the example. So, we can take different example of histogram representation here. If we consider a dark image, the histogram is placed at 0. We know to represent the pixel value in x-axis we will take the input pixel value, and this input pixel value will vary from 0 to 255. So, 0 represents black and 255 represents white. So, in a dark image, the histogram is placed at 0, or we can say it is grouped at black values. This represents the image consists of more black pixels compared to other gray level values. In the same way, if we consider the bright image, the histogram values are placed towards white or 255. That indicates the given image is having more white pixels compared to other gray level values. If we take low contrast image, you can see this is the example of low contrast image. The histogram is placed at the center, and if you take the high contrast image, the histogram is placed on entire plane. This placement of histogram in entire plane, we call that as the flat profile of histogram, which means for a high contrast image or a good quality image, the histogram values will be distributed on entire plane. So, from this we can say to get a high quality image, to get a high contrast image, the histogram value should be distributed on entire plane, or it should be having a flat profile. Histogram is used for various image processing applications like manipulating the contrast value and also brightness of the digital image. The histogram can control the quality of an image by normalizing the histogram values to a flat profile. So, to get a high quality image, the histogram value should be normalized to a flat profile, as you can see in this example. Let us take an example to understand histogram equalization. Let us take this input image with different pixel values. In the previous lecture, we understood about histogram equalization, and histogram equalization is a good approach because the method of implementation of histogram equalization is very simple. So, histogram equalization was a very simple method to implement. Histogram equalization is not applicable for some applications. So, we can say histogram equalization is not a best approach for some applications because histogram equalization is applied to entire image. So, it is not suitable if we wish to enhance a specific region of an image. So, if we want to enhance a specific region of an image, so we can't apply histogram equalization. That is why we will go with a new approach, which is histogram matching, which is also known as histogram specification. Histogram matching or histogram specification is a method that is used to generate a processed image that has a specified histogram, which means the goal of histogram matching is to take an input image and generate an output image that is based upon the shape of the specific histogram or reference histogram. So, generally we can say if we have histogram 1 and histogram 2, so we need to match histogram 1 with histogram 2. This figure shows how histogram matching can be achieved. Here the mapping is done from R of k to S of k. We know in the x axis we are having the input image pixels and in the y axis we are having output image pixels. So, this is the transfer function based upon the equation S is equal to T of R. Here we are matching R of k value with S of k. First we will take R1 that is matched with S1, then we will take R2 that will be matched with S2, and so on. We will match a pixel Rk with Sk. Now we will take one more transformation, which is g of z. This is the transformation function that is obtained from the probability distribution function values of R of k. So depending upon the values of R of k, which is the probability distribution function of R of k, g of z is designed. Here a pixel value zq is mapped with vq. If we compare these two diagrams, if vq value is approximately equal to sk value, we can take the inverse transformation and we can map sk with this z value. So that is what the histogram mapping is happening here. Here if vq value is same as sk value, then we will take the inverse transformation and map this s value with z. So this is what it is happening here. Sk is mapped with zk. So the name is given as zk because it is mapped with sk. So this is the same value as z. So what is happening here? If we take this transformation in this graph itself, let us write here, and this is the point where it is intersecting. Let us say this as zq. If you see here, if we map rk, we are getting sk, and for zq also we are getting sk here. So that's why instead of mapping sk to rk, we will take the inverse transform and map it to zq. So that is the process that is happening here. So sk is mapped to zk, taking the inverse mapping. To understand this graph, let us take a simplified example. Let us take an histogram of an image, and let us take one more specified histogram or reference histogram. So these two histogram values should be mapped. Now let us say if we perform histogram equalization on this transfer function, we will get a flat profile like this. Again, if we perform histogram equalization on this transfer function, we will get a flat profile like this. Now the histogram equalization value of this input histogram and the specified histogram are similar. That is why to map the input histogram value with this specified histogram value, we will perform histogram equalization, then the inverse of that histogram equalization will produce the mapping with the specified histogram. For example, let us say the value here 9 is mapped to 12 in the histogram equalized flat profile. Let us say for this some value, let us say for example 20 is also mapped to 12. So what we can do, 9 can be mapped to 12 and 20 can also be mapped to 12. That is why we will take the histogram equalization of 9 that will produce 12, and we can take the inverse of this value to get the value as 20, and we can map 9 to 20. So this is the process that is happening in histogram matching. Now let us understand the example of histogram equalization. So here we will take an image which is very dark image. So this is the photo that is taken by NASA. So this image is a very dark image, and if we take histogram of this image, we will get the histogram values that will be placed at 0. 0 is nothing but black. So this specifies this image consists of more black pixels compared to other pixel values. Now this image is not clearly visible. If we perform histogram equalization on this image, so we will get this output. So this is the transfer function of histogram equalization. If we observe after histogram equalization, we will get a bright image that is again not clearly visible. We call this image as washed out image. So this is the histogram after equalization. So to overcome this problem, we will go with histogram matching. In histogram matching, we will take a reference transfer function. For this reference transfer function, we will take the histogram equalization. Once we get the histogram equalization of this transfer function, we will take the inverse histogram values. You can see, so this graph 2 represents the inverse histogram values of this graph 1. Now we will map the input pixel values with this inverse value to perform the histogram matching. So this is the result of histogram matching. So after performing histogram matching, the image is clearly visible. If you compare with these two images, this is having a clear visibility. So this is one of the example of histogram matching. This is about histogram matching. Hope you have understood the topic. Thank you. In this lecture, let us understand smoothing spatial filters. Smoothing spatial filters are generally used for blurring and noise reduction. So to perform the operations like blurring and noise reduction, we can use smoothing spatial filters. Blurring is generally used in pre-processing, such as removal of small details from an image prior to object extraction. So blurring is done in pre-processing, which means before processing an image, we will do the operation of blurring. So blurring is done to remove some small details from the image before some processing. Noise reduction can be accomplished with the help of blurring with a linear or non-linear filters. So we can use linear filters or non-linear filters and use the technique of blurring to reduce the noise. Now let us see smoothing linear filters. The output of smoothing filter using linear spatial filter is simply the average of the pixels contained in the neighborhood of the filter mask. So if we consider a mask, if we take the average of these pixel values, so we will get the smoothing operation. These filters are also known as averaging filters because we are taking the average, and it is also known as low pass filters. This figure shows the example of 3x3 smoothing filter mask. You can use 5x5 filter mask, 7x7 filter mask, 9x9 filter mask. So you can take the odd values of these and you can take the smoothing filter mask. So here we are considering 3x3 smoothing filter mask. In figure A, the filter mask is having 3x3 values. So 3x3 it will be 9. Hence, to normalize or to get an average value, we will divide each coefficient by 9. So 1 by 9 multiplied with all these values is nothing but similar to dividing all these coefficients by 9. In figure B, if we add all the coefficient values, we will get 16. Hence, to normalize or to get the average value, we will divide each coefficients in this filter mask by 16. So this is a standard average filter mask, and this is known as the weighted average filter mask. The smoothing or filtering is the process of replacing each pixel in an image by the average of gray levels in the neighborhood, which is defined by the filter mask. So this will result in a sharp transitions in gray level value. Each pixel value in an image will be replaced by the average gray level values of the filter mask after performing the operation. One of the most common application of smoothing linear filter is to reduce the noise in an image. Smoothing linear filter has one of the side effect where they blur the edges. Edges are the desirable features in an image or very important feature in an image. These edges are characterized by sharp transitions in gray levels. Here figure A is an example that produces the standard average of pixel under the mask. So it is actually computationally more efficient to have the coefficient values as 1, and at the end of the filter processing the entire image is divided by 9. Generally, if we take m cross n mask, it will be normalized to a constant value which will be equal to 1 by m cross n. Similar to this value 3 cross 3, it is normalized to 1 by 3 cross 3, which is nothing but 1 by 9. A spatial averaging filter in which all the coefficients are equal are sometimes known as box filters. Figure B is the example of weighted smoothing filter. This filter will produce the weighted average. Here, each pixel values are multiplied by different coefficients, giving more importance to some pixels. The pixel at the center of the mask is multiplied by a higher value compared to the other pixel values, hence giving this pixel more importance in calculation of average. So this strategy is used to reduce the blurring during the smoothing process. The general implementation for filter with image m cross n and mask small m cross small n is given as g of x comma y is equal to summation of s is equal to minus a to a, summation of t is equal to minus b to b, w of s comma t into f of x plus s comma y plus t divided by summation of s is equal to minus a to a, summation of t is equal to minus b to b, w of s comma t. So here w of s comma t represents the coefficients of filter and f represents the coefficients of the image gray levels. Since you are dividing with the coefficients of filter mask, you will get the average value or you will get the average filters. This is about the smoothing filters. Hope you have understood the topic. Thank you. Understand sharpening of spatial filters. The principal objective of sharpening is to highlight the finite details in an image or to enhance the detail that has been blurred either in error or as a natural effect of particular method of image acquisition. So the basic objective is to highlight the details in an image or to enhance the detail that has been blurred. It has wide variety of applications including electronic printing, medical imaging, industrial inspections and autonomous guidance in military systems. In the previous topic, we understood that the image blurring can be accomplished in a spatial domain using pixel averaging. Since blurring can be done using integration, so sharpening can be accomplished or can be obtained by spatial differentiation. Hence, image differentiation enhances the edges and noise and de-emphasizes the areas with slowly varying gray level values. So this is the advantage of image differentiation. Now let us see the basic foundation of image sharpening. In this discussion, we can consider some details of sharpening filters that are based on first order and second order derivatives. First, let us consider the fundamental properties of derivatives. Derivatives of a digital function are defined in terms of differences. There are various ways of defining differences. The definition used for first derivative must be 0 in flat segments, must be non-zero at onset of an gray level step or ramp, must be non-zero along the ramp. So this we will understand when we consider the example. For time being, remember these properties for first order derivative. Similarly, we can define for second order derivative. It must be 0 in flat areas. This is the property of second order derivatives. Must be non-zero at onset and end of the gray level step or ramp, and must be 0 along the ramp of constant slope. So Remember these properties. We will take an example where you will understand what is a ramp, what is the flat segment. Since we are dealing in a digital quantities whose values are finite, the maximum possible gray level change also is finite, and the shortest distance over which the change can occur is between the adjacent pixel. If you consider an image with different pixels, the shortest distance where the gray level change can occur is between the adjacent pixels. Now let us see the basic definition of first order and second order derivative. The first order derivative of one dimensional function f of x can be given as delta f divided by delta x is equal to f of x plus 1 minus f of x, and the second order derivative can be given as delta square f divided by delta x square is equal to f of x plus 1 plus f of x minus 1 minus 2 f of x. For example, if we consider this pixel as f of x, the next pixel value will be f of x plus 1. The previous pixel value before this pixel is f of x minus 1. So, we can use these values in this definition and we can define the first order derivative and second order derivative. So, f of x plus 1 minus f of x. So, this value minus this value will give first order derivative. In the second order derivative, f of x plus 1 plus f of x minus 1 minus 2 f of x. So, using these three values we can define second order derivative. These two are the definitions that satisfies the conditions of first order and second order derivatives. Now, let us consider an example to understand this. To highlight the fundamental similarities and differences between first and second order derivative, let us consider an example. Here figure A shows a simple image. Figure B is the one dimensional horizontal gray level profile along the center of the image. So, in the center of the image, if we take a horizontal line, on this horizontal line we will have different pixel values. So, this profile specifies these pixel values, which is a one dimensional horizontal profile. Figure C is the simplified profile of figure B. Here we are having an image strip. This image strip is having different values. Those values are the pixel values along this line. So, you can see there are different pixel values. So, according to those pixel values we have written the gray level profile and we got this simplified profile. Now, let us find the values for first order derivative and second order derivative. The first order derivative defines that f of x plus 1 minus f of x. So, if you consider this value, this is f of x and this is f of x plus 1. So, from the definition it is 4 minus 5, it is minus 1. In the same way we can find for other values also. 3 minus 4 it is minus 1, 2 minus 3 it is minus 1, 1 minus 2 it is again minus 1. Likewise 0 minus 6 it is minus 6, 1 minus 3 it is minus 2. Likewise we can find the values for first order derivative. To find the values for second order derivative, so we can use the definition as f of x plus 1 plus f of x minus 1 minus 2 f of x. So, if we consider this as f of x, this will be f of x plus 1, this will be f of x minus 1. So, f of x plus 1 plus f of x minus 1 minus 2 f of x. So, it is 4 plus 5, it is 9 minus 2 times 5, it is 10, 9 minus 10, it is minus 1. So, in the same way 3 plus 5 minus 8, it is 0. In the same way 2 plus 4, which is 6 minus 6, it will be 0. Likewise, you can find different values for second order derivative. So, you can take here 0 plus 0 minus 12, it is minus 12. Again here 1 plus 1, it is 2. minus 6, it is minus 4. Likewise, you can find different values. Now, let us consider the properties of first order derivative and second order derivative, and let us trace these values from left to right. First, we note that the first order derivative is non-zero along the entire ramp. So, on this profile we have defined different shapes, which is ramp, which is isolated point or noise, flat lines are known as flat segment, and this is known as step. So, in the first order derivative along the ramp, it is non-zero, which satisfies the properties of first order derivative. The second order derivative is non-zero at onset and at the end of the ramp. So, this is the onset. Onset means the starting point of the value, and offset is the end point of the value. So, the second order derivative is non-zero at the onset of the ramp and also at the end of the ramp, which satisfies the property of second order derivative. So, from these two analysis we can conclude that the first order derivative produces thick edges and the second order derivative produces much finer one or much finer edges. So, if you see the isolation point, here the response is much stronger for second order derivative than the first order derivative. Hence, we can say the second order derivative enhances the fine detail, including the noise in an image compared to the first order derivative. If we consider the gray level step, the response of first order derivative and second order derivative are same. So, in conclusion, we can say that the first order derivative generally produces thicker edges in an image. The second order derivative has strong response to finite details such as thin lines and isolated points in an image. The first order derivative generally has a stronger response to gray level step. The second order derivative produces a double response at the step change in the gray level. So, if you see here, the step change is happening here. So, it will produce a double response. So, for first order derivative it is minus 6, second order derivative it is producing minus 12. Again here at the step change, the first order derivative is producing minus 2 and the second order derivative is producing minus 4. These are the few conclusions. We will continue this topic in our next lecture. Hope you have understood this topic. Thank you.
Hello friends, welcome to EC Academy.
In this lecture, let us understand sharpening of spatial filters. The principal objective of sharpening is to highlight the finite details in an image or to enhance the detail that has been blurred either in error or as a natural effect of particular method of image acquisition. So, the basic objective is to highlight the details in an image or to enhance the detail that has been blurred. It has wide variety of applications including electronic printing, medical imaging, industrial inspections and autonomous guidance in military systems. In the previous topic, we understood that the image blurring can be accomplished in a spatial domain using pixel averaging. Since blurring can be done using integration, so sharpening can be accomplished or can be obtained by spatial differentiation. Hence, image differentiation enhances the edges and noise and de-emphasizes the areas with slowly varying gray level values. So, this is the advantage of image differentiation. Now, let us see the basic foundation of image sharpening. In this discussion, we can consider some details of sharpening filters that are based on first order and second order derivatives. First, let us consider the fundamental properties of derivatives. Derivatives of a digital function are defined in terms of differences. There are various ways of defining differences. The definition used for first derivative must be 0 in flat segments, must be non-zero at onset of an gray level step or ramp, must be non-zero along the ramp. So, this we will understand when we consider the example. For time being, remember these properties for first order derivative. Similarly, we can define for second order derivative. It must be 0 in flat areas. This is the property of second order derivatives. Must be non-zero at onset and end of the gray level step or ramp, and must be 0 along the ramp of constant slope. So, remember these properties. We will take an example where you will understand what is a ramp, what is the flat segment. Since we are dealing in a digital quantities whose values are finite, the maximum possible gray level change also is finite, and the shortest distance over which the change can occur is between the adjacent pixel. If you consider an image with different pixels, the shortest distance where the gray level change can occur is between the adjacent pixels. Now, let us see the basic definition of first order and second order derivative. The first order derivative of one dimensional function f of x can be given as delta f divided by delta x is equal to f of x plus 1 minus f of x, and the second order derivative can be given as delta square f divided by delta x square is equal to f of x plus 1 plus f of x minus 1 minus 2 f of x. For example, if we consider this pixel as f of x, the next pixel value will be f of x plus 1. The previous pixel value before this pixel is f of x minus 1. So, we can use these values in this definition and we can define the first order derivative and second order derivative. So, f of x plus 1 minus f of x. So, this value minus this value will give first order derivative. In the second order derivative, f of x plus 1 plus f of x minus 1 minus 2 f of x. So, using these three values we can define second order derivative. These two are the definitions that satisfies the conditions of first order and second order derivatives. Now, let us consider an example to understand this. To highlight the fundamental similarities and differences between first and second order derivative, let us consider an example. Here, figure A shows a simple image. Figure B is the one dimensional horizontal gray level profile along the center of the image. So, in the center of the image, if we take a horizontal line, on this horizontal line we will have different pixel values. So, this profile specifies these pixel values, which is a one dimensional horizontal profile. Figure C is the simplified profile of figure B. Here we are having an image strip. This image strip is having different values. Those values are the pixel values along this line. So, you can see there are different pixel values. So, according to those pixel values we have written the gray level profile and we got this simplified profile. Now, let us find the values for first order derivative and second order derivative. The first order derivative defines that f of x plus 1 minus f of x. So, if you consider this value, this is f of x and this is f of x plus 1. So, from the definition it is 4 minus 5, it is minus 1. In the same way we can find for other values also. 3 minus 4 it is minus 1, 2 minus 3 it is minus 1, 1 minus 2 it is again minus 1. Likewise 0 minus 6 it is minus 6, 1 minus 3 it is minus 2. Likewise we can find the values for first order derivative. To find the values for second order derivative, So we can use the definition as f of x plus 1 plus f of x minus 1 minus 2 f of x. So if we consider this as f of x, this will be f of x plus 1, this will be f of x minus 1. So f of x plus 1 plus f of x minus 1 minus 2 f of x. So it is 4 plus 5, it is 9, minus 2 times 5, it is 10. 9 minus 10, it is minus 1. So in the same way, 3 plus 5 minus 8, it is 0. In the same way, 2 plus 4, which is 6, minus 6, it will be 0. Likewise, you can find different values for second order derivative. So you can take here 0 plus 0 minus 12, it is minus 12. Again here 1 plus 1, it is 2, minus 6, it is minus 4. Likewise, you can find different values. Now let us consider the properties of first order derivative and second order derivative, and let us trace these values from left to right. First, we note that the first order derivative is non-zero along the entire ramp. So on this profile we have defined different shapes, which is ramp, which is isolated point or noise. Flat lines are known as flat segment, and this is known as step. So in the first order derivative along the ramp, it is non-zero, which satisfies the properties of first order derivative. The second order derivative is non-zero at onset and at the end of the ramp. So this is the onset. Onset means the starting point of the value, and offset is the end point of the value. So the second order derivative is non-zero at the onset of the ramp and also at the end of the ramp, which satisfies the property of second order derivative. So from these two analyses, we can conclude that the first order derivative produces thick edges and the second order derivative produces much finer one or much finer edges. So if you see the isolation point, here the response is much stronger for second order derivative than the first order derivative. Hence we can say the second order derivative enhances the fine detail, including the noise in an image compared to the first order derivative. If we consider the gray level step, the response of first order derivative and second order derivative are same. So in conclusion, we can say that the first order derivative generally produces thicker edges in an image. The second order derivative has a strong response to finite details such as thin lines and isolated points in an image. The first order derivative generally has a stronger response to gray level step. The second order derivative produces a double response at the step change in the gray level. So if you see here, the step change is happening here. So it will produce a double response. So for first order derivative it is minus 6, second order derivative it is producing minus 12. Again here at the step change, the first order derivative is producing minus 2 and the second order derivative is producing minus 4. These are the few conclusions. We will continue this topic in our next lecture. Hope you have understood this topic. Thank you. In this lecture, let us understand the introduction to image enhancement in frequency domain. In the previous lecture, we understood about the image enhancement in spatial domain, where there was direct manipulations of pixels of an image. In frequency domain, the image from spatial domain will be transformed into frequency domain, then it is processed. After processing, inverse transform is applied to bring back the image into spatial domain. In frequency domain, the filters are used for smoothing and sharpening of an image by removing high and low frequency components from the image. Once we apply the frequency domain filter, the change will take place on entire image or whole image unlike in a spatial domain where the manipulation was taking place pixel by pixel. So, in spatial domain manipulation was done by considering one pixel at a time. So, we used to manipulate this pixel, then next pixel was manipulated, then next pixel was manipulated in the spatial domain image enhancement. In frequency domain, once we apply the filter, the change will occur on entire image at a time. Coming to the types of filter, there are two types of filter. First type is low pass filter and second type is high pass filter. The low pass filter removes all the high frequency component from the image only to keep the low frequency component, whereas in high pass filter it removes low frequency components from the image and only keeps high frequency components. The low pass filter is mainly used for smoothing the image, which is nothing but blurring the image. High pass filter is basically used for sharpening the image. Since it is sharpening the image, after processing the image will not have much of the background. So, low pass filter is used to remove the noise from the image. Both low pass filter and high pass filter can be classified into three types. First one is ideal filter, second one is Butterworth filter, and the third type is Gaussian filter. We will study about frequency domain in detail in the next topics. Hope you have understood this topic. Thank you. Different steps for filtering in frequency domain. This block diagram represents the different steps that are involved for filtering in frequency domain. Here the image f of x comma y, which is in spatial domain, is pre-processed, then Fourier transform is applied on that image to get f of u comma v. So, this is the Fourier transform representation of the image f of x comma y. For this Fourier transform, filtering function h of u comma v is multiplied to get the function h of u comma v into f of u comma v. Once the processing is done, the inverse Fourier transform is performed to get the value g of x comma y, which is the enhanced image of f of x comma y. So, here some pre-processing work as well as post-processing work will be done. Now, let us understand different steps involved in this. In the first step, we will take the image f of x comma y of size m cross n. In the second step, to centralize this image, we will multiply the image f of x comma y with the value minus 1 to the power of x plus y. So, this work is known as pre-processing. Then Fourier transform is applied on this image to get f of u comma v. So, here f of u comma v is the Fourier transform of f of x comma y. So, this can be obtained by applying DFT. In the next step, the filter function h of u comma v is considered, which is the filter in frequency domain, and these two values will be multiplied to get g of u comma v, which is equal to h of u comma v into f of u comma v. So, that is what it is happening in this step. Then inverse Fourier transform is applied on g of u comma v to get g of x comma y. So, in the next step, we will get g of x comma y by applying inverse Fourier transform. For this, we will apply inverse Fourier transform. So, this image can be written as inverse of g of u comma v, again it is multiplied with minus 1 to the power of x plus y. So, this is the final filtered image or this is the enhanced version of the image f of x comma y. So these are the different steps that are involved in filtering in frequency domain. Hope you have understood the topic. Thank you. Understand image smoothing and sharpening using frequency domain filters. In the previous lecture, we understood about the frequency domain filters, where the filters in frequency domain removes the high frequency or low frequency component in an image. Also, we understood that filters in frequency domain can be classified into two types. First one is low pass filter and second one is high pass filter. Low pass filter removes the high frequency component and retains the low frequency component. The application of low pass filter is to smoothen the image. For image smoothing, low pass filter is used in frequency domain. High pass filter removes the low frequency components and retains the high frequency component. High pass filter in frequency domain is used to sharpen the image. So high pass filter in frequency domain is used for image sharpening. These two filters can be classified into three types. First type is ideal filter, second type is Butterworth filter, and third type is Gaussian filter. The first type of low pass filter in frequency domain is ideal low pass filter. The transformation function of ideal low pass filter can be written as h of u comma v is equal to 1 for d of u comma v is less than or equal to d naught, and it will be equal to 0 for d of u comma v is greater than d naught. Here d naught is non-negative quantity and d of u comma v is distance from points u comma v. So d naught here represents the non-negative quantity or non-negative value, and d of u comma v is the distance between the points u and v. So these two are any random points in a image. If we consider the image f of x comma y of size m cross n, at that case we can write d of u comma v is equal to u minus m by 2 whole square plus v minus n by 2 whole square. So this is the equation for d of u comma v. Now if we consider a waveform, let us say this is the signal. On this signal, the threshold value which we are taking is d naught. So for this, the transformation function will be 1 for the signal value less than or equal to d naught, and it will be 0 for signal value greater than d naught. So here, if you consider this waveform, the transfer function is 1 for the value less than d naught, and the transformation function will be 0 for the value above d naught, which means the high frequency components in this signal will be removed and only the low frequency components will be retained using ideal low pass filter. Ideal high pass filter transformation function can be written as h of u comma v is equal to 0 for d of u comma v is less than or equal to d naught, and it will be equal to 1 for d of u comma v greater than d naught. So the high pass filter transformation function will be 1 for the frequency above d naught, and for the lower frequency the transformation function is 0. The frequency below d naught, the transformation function will become 0. So the ideal high pass filter will pass only the high frequency component and it will remove the low frequency component. This is how the ideal low pass and high pass filter will work. The major disadvantage of ideal high pass filter and low pass filter is after processing will obtain the blurred edges. So, we will get the blurred edges after processing using low pass and high pass filter. If we get a blurred edges, which means if you take an image and we are having an object in an image, and if the edges are blurred, we can't differentiate between the object and the other data in an image. So, this is one of the disadvantage of ideal low pass filter and high pass filter. The second type of low pass filter is Butterworth low pass filter. The transfer function can be written as h of u comma v is equal to 1 divided by 1 plus d of u comma v divided by d naught whole to the power of 2n. And Butterworth high pass filter transfer function can be given as h of u comma v is equal to 1 divided by 1 plus d naught divided by d of u comma v whole to the power of 2n. Here the value of n varies from 0, 1, 2, 3, 4 and so on. As the n value increases, the Butterworth filter will act as the ideal filter. Hence, n value should be maintained low or less so that we can remove the blurring of edges and edges can be defined clearly. So, the advantage of Butterworth filter in both low pass and high pass is useful in defining the edges in an image. So, to overcome the disadvantage of ideal filter, we can go with the Butterworth filter. The next type of filters are Gaussian low pass filter and Gaussian high pass filter. The transfer function can be given as h of u comma v is equal to exponential to the power of minus d square u comma v divided by 2 d naught square. For high pass filter, we can define it as h of u comma v is equal to 1 minus exponential to the power of minus d square of u comma v divided by 2 d naught square. The advantage of Gaussian low pass filter is that it removes low frequency noise, and the advantage of Gaussian high pass filter is that it removes high frequency noise. So, this is the advantage of Gaussian low pass filter and Gaussian high pass filter. So, this is about the image smoothing and sharpening using frequency domain filters. Hope you have understood the topic. Thank you.